Okay, so let's get started from last session. Uh, at the end of last session, we have finished the F distribution, with central version and non-central version. And now we are going into a Rayleigh distribution. The Rayleigh distribution is obtained as a PDF of X, where X is in fact equal to square root of x1 uh, square plus x2 square, and then x1 is the Gaussian distribution with zero mean and sigma square. And also we can also the for the x2 is the Gaussian distribution with zero mean and sigma square, and x1 and x2 are independent. Okay, so its PDF is expressed in this form, and again, uh, its domain is smaller than when it's smaller than zero. Its distribution is equal to zero, and then when it's larger than zero, then it will be x divided by sigma square exponent parentheses of minus 1 over 2 sigma square x square. And then this is the Rayleigh distribution. Then it's shown in figure 2.8 for sigma square equal to 1. And then we're always interested in the mean and variance of a random variable. So the mean will be expect of x equal to square root of pi sigma square over 2, and variance will be parentheses 2 minus pi over 2 parentheses multiplied by sigma square. And then the right tail probability is to integral this p of x from x to infinity, sort of a right hand side. Okay, so it's like we are but doing integration from a point on up to infinity. So that's the right tail, Now then it's easy from this. So if you take a right tail integration of this from x to infinity, then you get a closed form of exponential exponential um, this exponential x squared minus 2 sigma squared. Okay, so the Rayleigh distribution is related to the chi-square PDF, since if x is a Rayleigh random variable, then x is equal to square root of sigma square y, where y is distributed by chi square with degree 2. What it means is that if x is a Rayleigh random variable and y is distributed this way, then they are related by this equation, and this can be proven. Uh, Except that we are not doing it here, but it can be proven. And as a result, the right tail probability can be related as probability of x larger than something. That's the right tail probability from square root of gamma prime equal to probability of x divided by this. The reason that we divide this by that is because if they are related this way, think about it. We like to eliminate the square root of sigma square. We like to eliminate this term first. So we divide this x by this. Then that thing will be equal to square root of y. Think about this. This square root has a sigma square inside, so we divide it out here, divide it out. Then it becomes square root of y only. Of course, then at the right hand side, then you have to do the same thing, divided by sigma square. Okay, then it will be PR square root of y larger than square root of gamma prime divided by sigma square. Then it will be PR, this thing, take the square of it, you get y larger than gamma prime divided by sigma square. Then it will be what? This is chi squared with degree 2. Then you have q function of chi square degree 2. You have the q function of the chi square because the q sub chi square represents the right tail of y, right? The right tail of y. So now it becomes a q sub chi square parenthesis of this, and this goes to here, goes to here. All right, and then there's a square root here, so there is a no square root. If we put r here, then it's a r square here. So the difference is this we take the square of this, then it goes to here. So if we like to know PR x larger than gamma, then it will be equal to q of this, then gamma, this, let me just pronounce gamma, okay. Gamma square divided by sigma square, sigma square. Okay, then that will produce this thing, 2.23, 2.23. Since this is equal to that, so you just plug this term into x. You plug this term into x, then you get e exponent of a something, which is exponent of something here. So you put this into here, then this thing becomes this thing. Okay, so that is the Rayleigh distribution. And then for sigma square equal to 1, you can take a look at the probability density function, and the probability density function is in fact the looks like this. And of course, if you do sigma square equal to 2, you expect this to be more spread out because sigma represents sort of the variance here. See the variance here, the variance. So if you increase the variance, then you get larger dispersion. Is sort of spreading out density. So you get something shorter but spread out like something like this, spread out, and even more and more spread out. Okay, that'll be ready. Now let's take a look at the next one. Next one is Rayleigh. The Rayleigh distribution is obtained as the PDF of x equal to square root of x1 squared plus x2 squared, where x1 is equal to Gaussian distribution of mean 1 sigma square. x2 is distributed by n of mu2 sigma squared. Let's see the difference. This is sigma squared and sigma squared, and they are independent. That is Rayleigh. Okay, and then for this we still have the same variance, except the mu2 and mu1 are different. They are no longer zero mean. They becomes non-zero mean. So we take a look at the probability density function where p of x equal to x divided by sigma squared exp square bracket this, and then minus 1 over 2 sigma squared parentheses x squared plus alpha squared I0 parentheses alpha x divided by sigma squared for x larger than 0, and then for x smaller than 0 it's 0. So it's the same as chi-square distribution and then Rayleigh distribution. It's all 0 for x smaller than 0, and then for x larger than 0 it's all in certain form. Then let's take a look. If you are given x1 and x2, that means uh, mu1 and mu2 are given, sigma are given, and so this is supposed to be known because it's given. Then x is the argument. So we don't have problems with the x here. Sigma squared is given, but we have problems with alpha, right? Because alpha is not defined yet. I0 is not defined yet. So let's look. Alpha squared is equal to mu1 squared plus mu2 squared. So it's derived from this parameter that is given in x1 and x2. So now we get this as the alpha squared. So now alpha is fine. I0 is given in this form. I sub 0 of u equal to 1 over pi integral 0 to the pi, then exponent of parentheses u cosine theta d theta, which is equal to, it's a change of variable, not a big deal, not a big deal, just a change of variable. So it goes to from 0 to 2 pi exponent of u cosine theta d theta divided by 2 pi. Okay, then some examples will be given in figure for sigma square equal to 1, and then for some examples, and we'll look at that later. We'll take a look at that later. Then for alpha square equal to 0, it reduces to the Rayleigh. Is it true? Let's take a look. If alpha square is equal to 0, then you don't have any choices because mu1 is 0 and mu2 is 0. That's the only solution for alpha equal to 0. So if alpha square is 0, then mu1 is definitely 0. Mu2 is definitely 0. Then you have 0, 0 here. So let's go back and look. You see 0 here, 0 here. Now we have 0 here, 0 here. All right, okay, so that's sort of the concept of degenerate. The concept of degenerate is that when something is more complicated and it has some parameters that are simplified, then it degenerates to a simpler version, a simple version of itself. So you can see that if we assume mu1 and mu2 to be 0, then Rayleigh is actually degenerating back to Rayleigh. So what that means is Rayleigh is a special case of Rayleigh. Rayleigh is a generalized version of Rayleigh. So that's the idea behind it. So now we come back a little bit. I sub 0 is defined this way. So now it's defined. It's just a complicated equation, and we give it a name. Okay, we just give it a name as I0. Okay. Okay, then let's look. We'd like to know the probability density, not the probability density function, but the right tail, PR, probability of something, probability of x larger than square root of gamma prime equal to probability of something, and that x1 squared plus x2 squared divided by sigma squared, and then you take the square root of it. You take the square root of it. You take the square root and then divided by sigma squared. How come? How come? X by itself is the square root of this. So this part is just equal to X. We don't have problems with that. Now you don't sort of like to do some normalization. So you divide it by sigma squared. And then of course the right hand side gamma prime has to be divided by sigma squared inside the square root. Okay, then it's equal to this because you just take the square. You take the square of this, take the square of this, then the square root disappear. Square root disappear. So if the square root disappear, it becomes x1 squared plus x2 squared divided by sigma squared. Gamma prime divided by sigma squared. Alright. And then that's the probability of this. Then again, what is this? This is actually a non-central chi-square with degree 2, right? Recall the chi-square is a summation of Gaussian square. So this is summation of Gaussian square, right? So it's actually a, a, a degree 2 chi-square, non-central. So now we have this with lambda, and then for this to be larger than that, it will be q, because we have defined this before. So it will be q chi-square prime of lambda of this whole thing comes to here. Okay, or if you like to write it this way, it will be x larger than gamma equal to q, then q chi-square lambda of this. The difference is just not a big deal, really. Let's look. You have square root of this. Now we don't have a square root, so it becomes, if you have a square root, it goes to degree 1, right? Gamma prime to degree 1, order 1. And now we have gamma, then it becomes order 2. So we have PR x larger than gamma, and then equal to q of this something. And of course, the lambda is the 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 sum of the squares of the mean except is divided by sigma square, so it has a division. It has a division of sigma square. So lambda is this thing divided by sigma square. Then of course, then you can use MATLAB, so on and so forth, to sort of implement that, calculate its numerical values. Okay, so now just to slow down a little bit so that people can follow. We're at page 32. We're at page 32. Okay, and then we go to quadratic forms of Gaussian random variables. It frequently occurs that we require the PDF of y equal to x transpose A multiplied by x. And notice that you have a transpose. When you have a transpose, that is a vector. Think of it as a vector. As I mentioned before, uh, we have multiple random when we have multiple random variables, we like to use a vector form to represent it. The reason for doing that is it makes it simple. The form will be simple. If you write it all out, it's fine, it's correct, but it's complicated. So here we have this x, which is n by 1 Gaussian vector. When we say n by 1, it is a column vector. It's something like this, column vector. First element, second element, third element, fourth element, so on and so forth. When we say 1 by n, it will look like this. First element, second element, third element, fourth element, so on and so forth. That is 1 by n. That's 1 by n. Okay, my cursor looks like a little bit fat. I think it's fine. It's fine. Yeah, I think it's readable. Okay, so you have a n by 1, which is like something like this. Then how about A? A is a n by n matrix. Okay, okay. So if you have a x n by 1 and you take the transpose, you take the transpose, you take the transpose, I'm sorry, you take the transpose, then what's going to happen? It becomes a row vector. It becomes a 1 by n row vector. So this is a row vector. This is n by n, and this is n by 1. Then the outcome is what? The outcome is 1 by 1. Okay, let me write it clearly. This one is 1 by n, right? This one is n by n. This one, this x is 1 n by 1. As a result, this cancel out, this cancel out, and the outcome will be 1 by 1. So it's a 1 by 1. That y is a 1 by 1. Then what is a 1 by 1 matrix? 1 by 1 matrix is in fact a scalar. It's a scalar. Okay, so we have explained the structure of the matrix, and then the Gaussian vector with x distributed by this. So x is like a not like it's exactly a column vector, and it's Gaussian with mu vector and C covariance matrix. So I mentioned, I think I explained what's the mu vector and c vector before, right? This mu vector is a column vector, while its first element is the mean of the first random variable. This is the mean of the second random variable. This is the mean of the third random variable, so on and so forth. And for C, if we have a C, C is something like this. Then we have a diagonal, that's the covariance of the first random variable, covariance of the second, covariance of the third, so on and so forth for a diagonal. For off diagonal, it will be covariance of the first and the second. That's called cross covariance because it's COV of x1 and x2 is COV of x1 x3, so on and so forth. So this is cross covariance. Okay, so we have y equal to this. Then in general, this is a difficult problem. However, there are a number of special cases that will be useful. They are, for example, A is equal to C inverse and mu is equal to 0. Then what that means is xt c minus 1x will be distributed by chi-square distribution. Okay, this is chi-square distribution with degree n, meaning that it is in fact a chi-square distribution that is the summation of n IID Gaussian random variables. Recall chi-square. Okay, recall it. Recall. Okay, I think I don't have to repeat too many times. It's a summation of standard Gaussian. Okay. And if A is C minus 1, which means it's a C inverse, and mu not equal to 0, then x transpose C minus 1x will be chi-square distribution with non-centrality lambda. Again, we recall it. We recall what we talked about at the chi-square with the non-central version of the chi-square, where mu is not equal to 0. Then chi-square will be chi-square with the non-centrality parameter lambda. Then since mu is not 0, we calculate its lambda, which is not that complicated though. You just take the expectation of this thing and you get something like that. So lambda is in fact just a mu vector transpose C minus 1 mu, right? And then if A is idempotent, a bit hard to pronounce, idempotent. Okay, so if it's an idempotent, which means that A squared equal to A of rank R. Rank R means that it has non-zero eigenvalues up to the R. So for example, you have a 10 by 10 matrix and rank 8. That means it only has 8 non-zero eigenvalues. Alright, okay, and then C is equal to I and mu equal to 0. And then of course this is also a very special case. And then you get X transpose A um, transpose A X distributed chi-square to the degree R, and then this is not actually a square, not a degree of square. It's used to represent chi-square distribution. Okay, so don't get confused. Think of it as but thinking of it as something square. That would be a mistake. That would be a mistake. Okay? This is just a notation to represent chi-square, and sub r means it has mathematical meanings. It has degree r. So let's say you have a 10 by 10 matrix with rank r. When you multiply it, the remaining random Gaussian random has only 8. So now you have degree 8, not degree 10. Okay, just be clear about this. You have 10, but it has only rank 8. At the end of the day, you get 8, degree 8, not 10. Alright, so this is some of the properties of this Gaussian random variables. Here is a figure 2.9, which is the Rician. So let's take a look at the Rician that looks like this, and we have sigma square. So as you see alpha square. Alpha square is related to the mean, related to the mean. Okay, so uh, alpha square, if alpha square is larger than the mean is larger, which means it's more outspreading, it's spreading out at the right hand side, at more at this side, with larger alpha. Alpha is small, then you get sort of more concentrated distribution. The probability is concentrated around the area, and then this is concentration at here and concentration here. With larger alpha, then it goes to the right hand side. Okay, and for 2.4, we are going to skip this. We are going to skip this. So uh, for anything that is skipped, we will not it will not be in the homework, and we're not going to do it in the exam, so don't worry about it. When we skip it, we'll not do it in the exam, not in the homework. Okay, so let's skip 2.4. Some of the some of the additional chapters at the end of the chapter is just some additional simulation or numerical issues the author like to discuss, but uh, in the interest of time, whenever possible, we will just skip some of it just to simplify. All right. For example, here people are talking about how to do a Monte Carlo evaluation, things like that, but we skip it. We skip it. Okay, and as you can see in the problems, there are things that ask you to show, for example, a probability of some random variables larger than something. In fact, this is just a standard cube function, this Gaussian function, Gaussian cube function, except you have to do some transformation, and then transformation of a random variable, and you get something like that. Yeah. So you see some homeworks is asking you to sort of verify, double check uh, some of the concepts that we discussed in class. And then appendix, recall in last class I talked about when you do Monte Carlo trials and what are the things that you need to be aware of. The first thing is the rare event, right? The rare event, you like to get sufficient number for the rare event. The second thing is a statistical stability, which means that you do it the first round, you get this number, and then you do it the second round, you get a second number. You like those numbers to be somewhat identical. If they are not identical, or if they are far away from each other, then you know your number is not sufficient because they are not stable. You do it the first time, you get 10. You do it the second time, you get 20. That is not accurate, not stable, right? If you do it the first time, you get 10. You do it the second time, you get 9.99. You do it the third time, you get 10.0001. I think that would be reasonable because everything you do, the outcome is similar. That would be good, right? So that's the things that they discuss here. Of course, there are mathematical arguments about this, but again, this is skipped. We're not going to do it in the exam, neither in the homework. And then the next thing we are going to do is we are going to go to chapter 3. Chapter 3. Okay, so now formally we will go into statistical decision. All right, I think I will just take a break for this session and then we'll continue on chapter 3 next session. Right, take a break.